All right, some comments just in general, things that would help me as I'm grading. And if I'm happy when I'm grading, you get a better score. Not necessarily, but so number one, space your work out. And box your answers. If on a page, like you work 3.2 and it's totally dense here, and then 3.3 is like here, and 3.4, it's all crammed together, it's hard to find what I'm looking for. Spread it out. It also helps you practice making it neat so that when you look at it, you can figure it out later on. So please do that. Make sure you're showing details of your work. When I go through the homework in class here, I point out the things often that I'm going to be looking for. Just make sure you show the details. Like we had a problem where we had a pressure altitude and a density altitude, and is not as acceptable as you writing H sub P equals 33,500, and then an arrow or something saying, well, that's where I got this. There's the data. There's my answer. Here's the data. And then there's the density I got from that. So show it, show what the information was that you got, and then how it led to the answer. As I asked for on the quiz, you should say, well, I got this from Appendix B, standard atmosphere. And then on your file names that you upload, let's conform to this. Do your last name, underscore, first name, and then say homework 3. Sometimes the file shows up. We talked about this last time. In this last homework, I'd say almost all but 3 or 4 showed up so I could edit them in Blackboard. If for some reason your file gets jumped over and I have to open the file in Adobe, then I have to save it on my laptop. If you've already named it with your name, then it's easy for me to connect it back to your grade and upload that to Blackboard. Feedback on the homework is inside Blackboard. So I've actually written on the file that you uploaded in Blackboard. If I had to edit it outside in Adobe, then it's a file that's attached to your homework assignment. And if you look in the feedback section, there will be a file with part or most of your name on there, and it will have my annotations on it. So that's where the grading is done on that. So questions about that? I want to make sure you know where to go look for feedback on the homework. Okay, good. There's a new homework assignment that's posted on Blackboard as of this morning. And it's due, you should work it by class time next Monday, so a week from today. And then you'll submit it officially on Wednesday, and we'll do a quiz on Wednesday. So the new homework, my eraser here. So and so you notice that the due dates in the homework vary. That's because I always want to go over the homework the day before, so I have to make sure we get through the lecture material so you can do the homework, and then we do the quiz and actually officially turn it in on the following day. All right, so last time we were talking about, let's see, I need to put this so that it can be seen, don't I? All right, so we were talking about compressible flow last time. And we were talking about the energy equation. And compressible flow. So where we want to go with that is that we want to be able to integrate that differential equation that we did last time between 2 points in a flow. So let's say we have an airplane wing, and maybe we know the flow out in front because we know we're flying standard atmosphere, so that gives us density, temperature, pressure, and we know our velocity. And then we trace a streamline, and we want to know the values at point 2, somewhere on top of the wing. So the equations that we're going to use, we have the first law of thermo. And we had it 2 ways in terms of internal energy and then in terms of enthalpy. And when you're writing this, make sure you are careful to do a script V here because this is specific volume. And last time we talked about how we were going to say it's adiabatic, which really means no heat transfer and no friction, which means it's reversible. So these two together, if you remember from thermo or you're doing it now in thermo, this is what we call isentropic. Because the 2 ways that energy, not energy, gosh, I've lost the word. Entropy. The 2 ways entropy can change is if you have heat transfer and you have irreversible flow. Yeah. The up here, specific, oh, what happened to it? It's specific volume. Yeah, sorry. If I get to writing too small, especially for the screen, please say something. Thank you very much. So this is isentropic flow. Entropy doesn't change, there's no heat transfer. And so we can set the heat transfer to 0 in both of these equations. And then we use our definitions of specific heat that relate energy changes to temperature changes and enthalpy changes to temperature changes. So that just says if I have that much temperature change, I get this much internal energy change or enthalpy change per unit mass. And I can stick these up into the equations for thermo, like that. And that's the big deal that we were dealing with, right? This is flow variables, pressure, density, essentially. Specific volume, density, pressure, but we had to get enthalpy and internal energy in terms of the temperature, because that's a flow variable. All right, so if we make that substitution, then we're going to get minus PdV equals this. Flip it over to the other side. We get VdP equals C sub P dt. So that's two equations that we got going on, the two different thermodynamic law equations. So really what we're doing is trying to work it out so we get additional equations, remember? So draw a border down here. So that's the second equation over there with the substitution. And then we can combine these and get rid of dt. Because then that's going to get us a relationship between pressure and specific volume, which is 1 over the density. And remember, the density is the extra unknown that we have that we need another equation for. So if we substitute in here, I'm going to take this, stick it over here, so we get VdP is equal to C sub P over C sub V, because I solved here. There's a minus sign. So I took this, stuffed it over there, put the C sub V in the denominator. And then we want to get the pressures on one side and the specific volumes on the other side. I'm going to do some algebra here. And you can see we're setting up this to integrate because we want to get the same variable on either side, so we can integrate from point 1 to point 2. And then this shows up all the time, this ratio of specific heats. So we give that a name, and it is called the ratio of specific heats, and it's set equal to a variable called gamma. So define gamma is equal to C sub P over C sub V. It's the ratio of specific heats. And it turns out this is a really important number for compressible flow. This number shows up everywhere in all the equations. All right, so again, we want to go from point 1 in the flow in a streamline to point 2. Again, it's steady flow, meaning that at a single point, it doesn't change with time. It can change as it moves, but if we look at it always on the same point on the wing, it's the same. It's one-dimensional because we only have one direction of changing. And so we have all of these little dPs that we're going to add up as we move, because this is saying, well, dP changes as we move along the flow, and all the little dVs, so that's integration as we add up all those little changes. So we're going to integrate from point 1 to point 2. So at point 1, we've got P1 and V1, and here we're going to have P2 and V2. And this equation, when we integrate it, it's going to tell us the relationship between those two. Sorry, we call that gamma, so just put a gamma there. It makes it a lot easier to write. And so fortunately, we've all taken calculus where we studied, well, what is the integral of dx over x? And that's the natural log. So it's evaluated at the limits. And now the rest is algebra. We know that if we subtract logs, we can take the log of the subtraction is the same as division inside the logarithmic. And then another property of the natural log, we're using a lot of math here, right? Remember, if you multiply, it's the same as exponentiating. And so this is a relationship between pressures and specific volumes, but we like densities. So we're going to write it in terms of densities, because in aerodynamics, that's what we like to deal with. And then raised to the negative power means we can flip it. And then since we have log on both sides, we can take the anti-log after we've done all this algebra. Oh, sorry, that minus is gone because I flipped it, right? And so this is called, there's a name for these when we talk about them, they're called the isentropic relationships. And if we use P equals rho R T for each of the pressures and densities and temperatures, we can actually get another relationship if you plug in for rho 1 here and rho 2. Then you got everything in terms of P's and T's, and then you factor the P's over to the other side and solve. You get temperatures here. And so it's just handy to include this in the formula. You can always use this formula to get density and then plug density and pressure into the ideal gas to get the temperature. But sometimes you want to just go straight from pressure to temperature, and so those are the equations. Well, that's a head full of information already, right? What did we do? We said, okay, we've got compressible flow, so density is now an unknown. And so we needed to add the first law of thermo. Because we needed another equation. And we know thermodynamics, sort of, because I don't know if I ever got a 100% grasp of the whole thing. But there's enough of it that I can do this. And the first law of thermo relates temperature, density. Well, it related density and pressure, right? The pressure was the work going in, and the density was in terms of specific volume. So we're good there. We just did a lot of work to integrate from one point of the flow to the other point to get this set of equations. All right, so I always talk about assumptions. This is the major assumption that goes with these equations. You're assuming no heat transfer, so there's no combustion, no burning of fuel. It's just flow around an object or through an object. And these are really handy. You may get a problem where you know the pressure and the temperature measured in the flow out in front of the airplane, and then you follow that flow over a wing, and you measure the temperature on top of the wing, and you want to predict, well, what is the pressure up there? And temperature is an easy thing to measure. You put a measurement device, a thermometer, you get it. And so we can use these relationships to find out what the pressure is on top of the wing, and then we can calculate the lift of the wing. Okay, so let's recap. How are we doing on time? Got another 10 minutes, all right. Oh, one other comment. In the book and other places, you'll see these things flipped around. In other words, you'll see this. Is that correct? It looks backwards. You got, well, P2's on top and P1's on the bottom. Well, two things. Whatever we call 1 and 2 points in the flow is totally arbitrary, right? So we could have called the point 1, the one further down, and point 2, the one up further. So it makes sense in that way. But also, if you look at this, this is this thing to the -1, right? And this is this thing to the -1. And if you flip this side and flip the other side of the equation, you get an equality still, right? So A equals B is the same as 1 over A equals 1 over B. And so both forms of that are correct. So in this case, it's not a big deal what you choose as point 1 or 2, although I like to choose 1 as upstream and 2 as downstream. It's just easier to keep track. All right, so let's recap. How do we solve flow problems in our one-dimensional steady-state flow? So for incompressible flow, here's what we have. So I'm going to do that over on this half. We have the conservation of mass, which says what goes in has to come out. And for incompressible flow, we can knock those out, and we get a nice equation that if we know areas and velocities, we've got it. If we need to calculate pressure, then a force equation is necessary, and that's Newton's law for fluids, or Bernoulli's equation, and that says so we got that, and that relates pressures and velocities. Makes sense, right? Newton's law relates forces and accelerations. This is a change in velocity, so that's an acceleration. So it's totally appropriate that if we deal with pressures and velocities, we use this. And that's Bernoulli's equation along a streamline. And then if we need it, but we typically don't, because we don't care to calculate the change in density, because we're saying density is constant. But if you need it, you also have the equation of state at any point in the flow. So if for some reason you want to calculate, if you know your pressure at 2 and they say what's the temperature and you know the density is constant, you stick that number in there, you stick your pressure in, and you can calculate your temperature if you want. And you can see why you would want to assume incompressible flow if you can, because those two equations and you're done. I guess if you really want to add another equation, it says ρ1 equals ρ2. All right, so now for compressible flow. It's more complicated. Philosophically, it makes sense. If you're standing still and there's no movement of the air, things are really easy, right? In fact, statics is easier than dynamics. So now the air starts to move, and as long as it's low speed, the cost of doing the calculations is not so much. We can do that. But if you want to go faster and faster, now it's harder and harder, and it costs us more in terms of calculations. So it's kind of like you have to pay for the faster you go, which makes sense. And so this is for compressible isentropic. We still have the conservation of the mass. Only now we can't knock out the density. So we have to calculate density. We still have the conservation of momentum. But it is not Bernoulli's equation, because Bernoulli's equation was for incompressible flow. We integrated that Euler equation. Density was constant. It was easy to integrate. Here, it's not so easy, and we need to show this, but I'm going to give you the equation just as a summary. So we still need to derive this one. But if we want to know velocities, this is the go-to equation. Notice it looks like Bernoulli's equation because you have the 1/2 velocity squared. But here we've got temperatures and there's no rho in there. So this allows us to relate velocity to temperature, and then the isentropic relationships allow us to take the temperatures and get density and pressure. And you still have the equation of state, although you typically don't need the equation of state because you got these here that relate pressure, temperature, and density, but you can write it down. So for any point in the flow, you can use those as well. So what I've given you now, and what we developed in our class, is we've added these to our toolbox for aerodynamics. So our aero toolbox. Not only do we have screwdrivers and wrenches and saws in our toolbox, but we understand the physics behind how those tools were built and what they really mean. And what you do when you do the homework is you're learning how to use these tools to predict aerodynamics. And so here's your toolbox for incompressible flow. Here's your toolbox for compressible flow. And then the next thing we need to talk about is the speed of sound and what happens when you go near, at, or faster than the speed of sound. So that's going to be next. We still have to do this, so next time we're going to deal with this equation. Where does that come from? And then we can solve high-speed flow problems. That's all I think I need to say today. Any questions, comments, thoughts about how the semester is going? Looking for fall break and we're not going to get it. But Thanksgiving break is forever. Not really. Thanksgiving break's a week, right? And then we have online classes after that, so. All right, I'll see you on Wednesday. Enjoy the rest of your day. Weather's nice, go outside, do something.